on screen can be seen, right?
Yes, clear.
Okay. Good morning, everyone. First of all, thank you for the opportunity given by all parties concerned so that I can make a presentation today at the International Conference on Heat Transfer, Energy and Mechanical Innovations 2022. My name is Michael Wijaya. I am from Laboratory for Engineering Design and Tribology, Diponegoro University, Central Java. And I will be presenting behalf of my fellow authors who worked this paper titled Thermohydrodynamic Analysis of Concentric Journal Bearing with Heterogeneous Slip-No-Slip Pattern. Before we dive right into the heart of it all, I will firstly give an outline on how this presentation will go. This presentation will be divided into 5 parts, as we can see on the screen. And now we will begin into the introduction. Journal bearing, the simplest type of bearing, which consists of just a bearing surface and no rolling elements. As it operates, the journal is able to slide over the bearing surface. The simplest example of this is a shaft rotating in a hole, as we can see in the below figure. Also to note, journal bearing needs lubrication. A film of lubricant exists between the shaft and the bearing in order to aid lubrication. Although simple, there are also challenges in the process of manufacturing a journal bearing. For example, the aim for increasing the load carrying capacity or for its ability to accommodate higher operational speed. All in all, to enhance the tribological performance. There are, however, factors that affect the performance of a journal bearing, say slip and cavitation, in which some previous work have been done concerning these specific phenomena. Example, Salant and Furtier in 2004 studied that the slip condition on a journal bearing could enhance its performance compared to conventional ones. And cavitation, studied by Lee in 2012, in which it enhances the load support of a journal bearing. So, what does it all even lead up to? The work done in this study has several objectives to be fulfilled. Firstly, to investigate the effect of THD or thermohydrodynamic lubrication and cavitation on journal bearings. Second, to examine the effect of induced slip on journal bearing tribological performance. Third, to examine the effect of induced slip on temperature distribution of a journal bearing. And last, to investigate the impact of shaft rotational speed variations on tribological performance and journal bearing temperature distribution. Now, onto theory. Load carrying capacity, or as we symbolize in the slide as capital W, is a value we get by integrating pressure distribution across the bearing surface. Theta, which represents circumferential angle, is an angular angle coordinate from the film with maximum thickness. P, Rj, and Dj have all been described as hydrodynamic pressure generated, journal radius, and journal diameter. And then there is dz. dz is an integral variable that has means to differentiate upon the z-axis. We will also be covering on the governing equations that bases the calculations which are required. First, the Navier-Stokes equation, which in fluid mechanics is a partial differential equation that describes the flow of incompressible fluids. In the third parenthesis, we can see the tau symbol, which stands for the stress tensor and can be expanded into the equation on the second light blue colored rectangle in the middle. In its solution, the Navier-Stokes equation requires the principle of conservation of mass. And for this specific reason, a continuity equation is needed, which can be seen in the pink triangle below. Onto cavitation. The cavitation models available in the ANSYS software are these three. And the Schneider-Sauer model is picked for this particular case, considering what previous studies in the similar field has been using and is considered ideal. The cavitation equation, all the symbols in it can be described. V, all the small v's, stands for vapor-liquid phase. Alpha, which appears twice, is the vapor-liquid volume fraction. PV, or we can read it as rho V, is the vapor-liquid phase density. Phi V is the vapor phase velocity. RE and RC is the value of mass transfer related to bubble destruction and bubble growth. Lastly, slip, the condition which is assumed to be at the boundary condition, where the fluid adjacent to the solid surface has a relative speed compared to it. What are the possible causes of slip phenomena? We can see on the second sentence below, when the solid surface is relatively smooth and the fluid is not strong enough to lubricate it, or when adhesion force is very minimal, slip can happen. And here are the geometric specifications of the journal bearing that is used in the study, with length, diameter, clearance, and eccentricity as described. We examined the bearing with a few varying journal velocities, ranging from 100 up to 5,000 RPM, with 0.04 thickness. And the fluid properties is taken from a similar study done by Lee in 2018. Also, the schematics of the slip zone on the journal bearing, with each symbol described as such. With zero eccentricity, half of the bearing surface is said to be the slip region. The region with black circles all around it is supposed to be the slip region, and the rest of it doesn't have slip boundary condition. Onto the results, journal bearing shaft speed variations with slip included. It should be noted that in the real application for a concentric condition, the lubrication failure will occur in the conventional bearing due to the absence of the additional load support. The hydrodynamic distribution of pressure with slip included is depicted in the figure, which shows us that as the shaft speed on the bearing rises, as the shaft speed increases from 100, 500, 1000, 3000, and 5000 RPM, so does the hydrodynamic pressure produced. The maximum hydrodynamic pressure rises due to an increase in the volume fraction of vapor created due to cavitation, which will be shown in another graph later on. As illustrated in the figure, an increase in shaft speed in the journal bearing induces an increase in the maximum temperature of the lubricant as well. It can also be observed that the temperature profile reveals the difference in values between the stationary and the moving wall. On the legend, labeled SW representing static wall and MW representing the moving wall. Which one are these exactly? We can go back to the schematic before. We can see on the above figure this tube-like geometry. Outside of the tube is what we mark as the stationary wall, part of the lubricant adjacent to the bearing surface. And inside of the tube is the moving wall, part of the lubricant which is adjacent to the rotating journal. Now, onto vapor volume fraction. Volume fraction of vapor also varies between different shaft speed variations. As previously mentioned, increase of the maximum hydrodynamic pressure is due to volume fraction. The particular reason for this circumstance is the cavitation phenomena itself. This actively demonstrates that cavitation contributes in the load carrying capacity value of a journal bearing. Now, we see the load carrying capacity of a conventional bearing with a bearing with slip-no-slip pattern. It is revealed that a heterogeneous slip-no-slip pattern produces the load carrying capacity, while for the conventional bearing, the zero load carrying capacity is achieved. This is for the reason that under concentric condition, no hydrodynamic pressure is generated. due to the absence of the wedge effect, due to absence of the wedging effect. This case doesn't apply when a heterogeneous slip-no-slip pattern is applied. The slip boundary leads to a reduced pressure gradient, which creates the pressure jump onto a higher value, hence increasing the load carrying capacity. The current study examines the THD, the thermohydrodynamic behavior of heterogeneous slip-no-slip journal bearings with key performance parameters such as the load carrying capacity, the temperature, and the hydrodynamic pressure. Also, the impacts of shaft rotational speed are explored, as well as the possible benefits of using a heterogeneous slip-no-slip pattern. And by that, these conclusions can be drawn. First, the assumption of isothermal in heterogeneous slip-no-slip bearing cannot be valid, considering the moving and stationary wall gives a different trend of temperature. Second, under the concentric condition, the heterogeneous slip-no-slip pattern gives a beneficial effect on improving the performance, while for the conventional bearing, the performance can fail. And that would be the end of the presentation. Thank you for everybody's attention. I will hand it over back to the MC or the moderator. Thank you.
Is there any
Yes.
comment?
Please. Yes, I have. Firstly, I will check your papers. I think it's good following the template, but later we need to again check the detail of the paper. But again, in this, I need you to emphasize your conclusion number one. The assumption of the isothermal of the heterogeneous or slip-no-slip bearing cannot be valid. Cannot be valid. Can you emphasize this one? How can you? What do you call? How can you draw the conclusion like this?
Okay. Thank you, Mr. Turnet, for the question. I will back to sharing my screen.
Yeah.
So the conclusion for number one, the assumption of isothermal is cannot be valid, considering the second figure that we show in slide number 13. So on this part, you can see the temperature distribution along the bearing circumference. And on the trend, we have two type of lines, the continuous lines and the dashed lines. The dashed lines representing the moving wall, while the continuous line represents the static wall. And by that, we can actually see the figure above here. We know that between the inner wall and the outer wall have different trend of temperatures, as we can see in this figure. So we cannot say that this is isothermal. An isothermal assumption cannot be valid, considering this static wall and moving wall gives off different trend. It was, I hope that answers the question, sir.
Okay. In this figure, you can see this figure temperature. So the peak will be about the angle 260 or something.
Yes, around 260.
260. Yeah. I think maybe you can also withdraw that as your conclusion, right? Because you can conclude that when you can add your conclusion based on the graph what you have got, right? So in your conclusion, you can give what we can say. Quantitative result. Okay, I think it's good paper.
Okay, thank you so much, Sarah Turnet, for this advice.
Yeah.
Okay, thank you, Mr. Tunat, and also Mr. Michael Wijaya. So for the second presenter, I would like to invite paper number 1037, Mr. Lang Parikasip.